Hi everyone! So today in this video we'll be talking about homogeneous differential equations. So far in class we've learned about differential equations where x and y are separable. However, that's not always the case. So today homogeneous differential equations is one of those times where you can't really separate them in terms of x and y, but it can be made separable by a change of variables. And by a change of variables, we usually mean y equals vx. So substituting y with vx, and we'll talk a little bit more about it in example 3. So homogeneous functions are expressed in the form of y prime is equal to f of x and y. So it's pretty straightforward. It's a function where there are two different variables. The function given by f of xy is homogeneous of degree n if f of tx and ty is equal to t to the n fx and y. So this is the original function. And also, by the way, n has to be a real number. So what this basically means is that when you substitute tx and ty for x and y, you'll get something that is just like the original function, but times t to a power of n. Still might seem a little confusing, but let's do an example. So the first step is always, in order for you to verify a homogeneous function, the first step is always to substitute tx and ty into the original function. So tx to the power of 2, ty minus 4, tx to the power of 3, plus x tx ty squared. Then we'll have to simplify it. So then pull out t to the power of 3, you'll get this. Now that everything is simplified, you can see that this part of the function is exactly the same as the original function. And it is the original function times t to a power of 3. So we can say that it is homogeneous with a degree 3. And that is your answer for the first verifying homogeneous function question. So for the second example, it's exactly the same procedure, only that the result is a little different. So the first step is still plugging in tx's and ty's. I'm skipping a step here, but you'll get something like this. So be careful, because this part is not exactly the same as the original function. In fact, this function is not homogeneous. Although it is t to some power, degree 1, but the other side of the function is not exactly the same as the original, so it is not homogeneous. Now for the third example, try it yourself. Pause the video for a second and then check your answers. And the answer is that it is homogeneous with a degree 1. So let's move on. Now, instead of talking about homogeneous functions, let's talk about homogeneous differential equations. So the definition of a homogeneous differential equation is that a homogeneous differential equation is an equation of the form m of xy dx plus n of xy dy. And that is all equal to 0. So also, by the way, m and n n needs to be homogeneous functions of the same degree. So what this basically means is that there are two homogeneous functions, something just like what we did before, something like this. There's two of them, and then adding them together gives us a answer of 0. And most importantly, actually, the two homogeneous functions have to be the same exact power. So when you substitute in tx's and ty's, it should get you the same power for t. So let's see for example 2. It's the same idea plugging in tx's and ty's. So I'm not going to write out everything, but basically this is for dx and then dy. So from here you can see that both are homogeneous functions and they both have a same degree of 2. So the next two are really similar. Do it yourself, pause the video, and then check your answers. So the answer for the first problem is that they are both of degree 2 and it is homogeneous. The second one is both with a degree of 3, homogeneous. The third one, I didn't even finish it, but as you can see, the first function is not homogeneous, so the answer is it's not a homogeneous differential equation. Now that we know the definition of a homogeneous differential equation, what can we do about them? How can we solve for them? Well, the change of variables for homogeneous equations does just that. If you remember from page 1, we've talked about how homogeneous differential equations are not separable in terms of x and y. However, it is separable if we do consider a change of variables. So for homogeneous differential equations, it can be transformed into a differential equation whose variables are separable by the substitution of y equals vx, where v will be a differentiable function of x. So basically what this means is that whenever you see a y in a homogeneous differential equation, you can substitute it with vx, and if there's a dy, you can substitute it with the derivative of the same equation. So let's take a look at the example. So in order for us to use the change of variables for homogeneous equations, we have to make sure that it is homogeneous before we do it. For this particular problem though, we don't really have to do that because we know that we're dealing with a homogeneous differential equation. However, if you're doing just practicing or when you're doing a test, maybe make sure to verify if it's homogeneous before doing the problem. Well, maybe we should get into the habit of verifying it. We don't really have to write anything down. However, I would suggest just by looking at it, make sure that it's homogeneous. Well, over here we can see that if you plug in tx and ty's, you'll get t to the power of 2. So it is homogeneous with a degree of 2. And then on this side, if you plug in tx and ty's, you'll also get a homogeneous function with degree 2 as well. So that basically means it is homogeneous differential equation. D means differential equation. So now that we know it's homogeneous, then we can start doing the problem. Well, the change of variables for homogeneous equations, remember, it basically says to plug in Vx for y's. However, you're not just plugging in y's, because on this side there's also a dy. We can't just leave it there, so we'll have to substitute that out as well. So let's find the derivative of Vx. Well, using the product rule, we'll get that v plus dv dx is the derivative. Remember that v is a differentiable function of x, so when you take the derivative, v's derivative is dv dx. And we're not just solving for dy dx, we're only substituting out the dy part, so multiply both sides by dx, we'll get v dx plus, make a note about that, plus dv. Now that we have both things that we're substituting, we can go ahead and just substitute it. So we have a y, that's the first part, and then substituting Vx again for y, dy. Oops, nope, remember to substitute dy with whatever you just got. It's always going to be the same if it's homogeneous. You could just memorize it. The next step is basically to simplify it and then get the same variables together. Remember that the goal is, again, to separate v and x to different sides, unlike the other differential equations that we did before where we separated x and y's. This time we'll be separating v's and x's, and then in the end we will substitute out v with y. So let's see. I'm skipping a few steps here, but basically just combining like terms. Remember that these two terms need to be on different sides, so remember to get rid of the parentheses here. And we will get 3x to the third v dv. And then take a look at the equation. There's x squared in all of the terms, so we can just cancel that. It's basically dividing both sides by x squared. Remember that here, over here, it's x cubed, so leave that last x. And then combining like terms again, should be plus sign x plus 3x v dv equals 0. And then separating negative 3x v dv. Divide this side by x, this side by x, and 1 plus 2v squared. So the x's cancel on the side, this whole thing cancels on the left, and we are left with 1 over x dx and negative 3v 1 plus 2v squared dv. We know how to differentiate these. On the left side, it should just be ln of x plus c. On the right, it's u substitution. U is equal to 1 plus 2v squared. Du is equal to 4v dv. Divide both sides by 4. We'll get negative 3. We'll pull that out from the integral. And then it's 1 over u du, which is equal to ln of u. On the left hand, I wrote this as c1 because c1 is just any constant. We can also write it in the form of ln. the ln of c is also constant, so these two are basically the same idea. Either one can be just any constant. That way it might be easier to simplify. Using a property, we can get that ln, this whole thing is just equal to cx, which looks a little bit cleaner. You don't have to do it, but it's a small trick. So the next step is pretty straightforward. So you should have gotten something like this. So the next step of this problem is to substitute v with in terms of x and y. So remember, going back to the really top, we substituted y with v times x. When we substitute out v, we'll substitute it with y over x. So basically dividing both sides by x. And with that in mind, cx, that's substituting v, will equal to 2 y over x to negative 3 over 4. So this was the answer from our notes. However, sometimes if you're doing a multiple choice, they won't have a answer like this with all the fractions. So, or sometimes if you want to match the back of the book, they usually don't have it like this. They have it without the fractions. So let's see how we can actually simplify this. I would suggest to get rid of the 4 over here to start off. To do so, take the power of 4 on both sides, so it will be c to the power of 4 is still c, so x to the power of 4 is equal to, this part is still the same. I'll get rid of the parentheses, so it's y squared minus divided by x squared, and all to the power of negative 3. And then we could multiply or divide both sides by the same thing, by negative 3. I'm not going to write out the same thing, but you get the idea. So we'll have c to the power of 4. If we divided it by a negative power, that basically means times with the positive power. So that will be positive is equal to 1. And we can divide both sides by c if we'd like to. You don't really have to. That is still going to be c. Next up, in order to get rid of the x squared on the bottom, we'll have to multiply it. And in order to do so, however, we'll have to multiply this whole thing with the power with x to the power of 6. Because although it's only x to the power of 2 in here, it has it go to the power of 3 again, so x to the power of 2 to the power of 3 is x to the power of 6. So we'll have to multiply both sides by x to the power of 6. Actually, no. Since we have the x to the power of 4 over here, we only have to multiply both sides by x to the power of 2. Which, over here, it gives us x to the power of 6. And then multiply that into that. X to the power of 6 turns into x squared. X to the power of 6 divided by 3 is x to the power of 2. I'll write that out actually. Plus 2. Y to the power of 2 is still the same, and x to the power of 2 are 3. Well, that is equal to 2, and that is also equal to 2, which, again, we can cancel out this as well, which leaves us to x to the power of 2 plus 2y to the power of 2 all to the power of 3 is equal to c x squared. And that will usually match up or will be similar to the back of the book. That is it for today. The suggested homework problems are down on the last page of the notes. Try out the ones that you feel like will help. I hope this video helped. Thank you very much. Thanks for watching.